Okay, my name is Putu Arindra, and we will discuss about the one of the chapter in the metallurgical, that is chapter 14, about the heat treatment of non-ferrous alloy. And my main reference is the book Metallurgi for the non-metallurgists, and now we will come next to the chapter 14.1. 14.1 Recovery and Recyclization Annealing. Annealing is a generic term used to denote a thermal treatment process that consists of heating a material to an ambient temperature and holding or soaking it for sufficient length of time at that temperature, followed by cooling at suitable rate. This practice is used primarily to soften metallic materials, but it's also used to produce specific changes in other property or in microstructure. When applied to relieve internal stress, the process is called stress relieving or stress relief annealing. Annealing is primarily a function of two main variables in non-ferrous alloy: the temperature to which the material is heated and the hold time at temperature. For steel alloy, the rate of which the alloy is cooled back down from the soak temperature is critically important factor during the annealing cycle, and this cooling rate may also be an important factor for specific non-ferrous alloy. When annealing is performed for a short period of the time or at low temperature, the hardness of cold work alloy remains relatively constant. These are true at level of temperature activation is not sufficient to significantly affect hardness during recovery. There is some movement and readjustment of dislocation during the recovery stage. That some property do change during recovery annealing. For example, the electrical resistivity of an alloy is typically increased by cold working, but can be recovered before annealing has a significant effect on hardness. 14.2 Heat treatable aluminum alloy. Rogue and cast aluminum alloy are commonly designed by a series originally developed by Alcoa. The series classified aluminum alloy by the principal alloying elements. The different type of aluminum alloy also can be classified as either heat treatable or non-heat treatable. The highest stress level are attained by the heat treatable alloy, which are strengthened by passively hardening as the mechanical property and strengthening mechanism. The non-heat treatable aluminum alloy include pure aluminum, aluminum manganese alloy, aluminum silicon binary alloys, aluminum magnesium binary alloys, and other mixed-selection of alloys. 13.3 The cobalt alloy. Cobalt is useful in applications that make use of its magnetic properties, corrosion resistant, wear resistant, and or strength at elevated temperatures. Biomedical application is another important use. The initial biomedical application of cobalt-based alloy were in the dental field, and early evaluation of these alloys show excellent wear resistance, corrosion resistance, biocompatibility, and mechanical property when is used before as orthopedic implants. Hardening mechanism for cobalt alloys involve solid solution strengthening, wall hardening, and solution threading and aging. The wear-resistant cobalt alloy, for example, the essentially COCRWC quartznized with chromium, providing strength and corrosion resistance to the solid solution in addition to functioning as the chief carbide forms during alloy solidification, tungsten provides additional solid solution strength. The attractive wear property of this alloy are attributed chiefly to the usual deformation characteristic imparted by cobalt. These include an ability of cobalt to transform under mechanical stress from an FCC to hexagonal closed peg or HCP structure, a high twinning propensity, and a low stacking fault energy. The carbides play a secondary role, being particularly important under condition conductive to low stress abrasion. 13.4 There is copper alloy. Copper can be hardened by solid solution alloying and by word hardening. The commonly used solid soluting alloy element lies in approximate under of increasing effectiveness are zinc, nickel, manganese, aluminum, tin, and silicon. In addition, a limited number of copper alloys can be strengthened by heat treatment. These are two general types of heat treatment used to harden copper alloys. The first one is the softened by high temperature quenching and hardening by low temperature precipitation hard treatment. These are hardening, quenching from high temperatures to Martin stick type reaction. 14.5 The magnesium alloy. The basic temper designation used to designate the various type of heat treatment for magnesium alloy include F as fabricate, O annealed, and recrystallization, H strength hardened, W solution heat treated unstable temper, T2 annealed, T3 solution heat treated and cold wall, T4 solution heat treated, T5 artificially aged only, T6 solution heat treated and artificially aged, T7 solution heat treated and stabilized, T8 solution heat treated, cold wall and artificially aged, T9 solution heat treated, artificially aged and cold wall, and T7 artificially aged and cold wall. Heat treatment can improve the mechanical property of most magnesium casting alloy. In most rock alloy, maximum mechanical property are developed through strength hardening, and these alloys generally are either used without subsequent heat treatment or merely aged to a T5 temper. Occasionally, however, solution treatment or a combination of solution treatment with strength hardening and artificially aging will sustainably improve mechanical properties. T6 is nickel alloy. Nickel is an austenite form and no allotropic phase transformation occurs in nickel or the high nickel family of alloys. The alloys are austenite from the melting temperature down to absolute zero. Nickel has a natural tendency to combine with sulfur and oxygen. It is found in nature as nickel sulfide and nickel oxide ores. In heat treating nickel or alloy nickel, it is critical to minimize exposure to sulfur in solid or gas from once embrittlement by sulfur occurs. The contaminant area must be removed by grinding or scraping. Nickel has very low solubility for carbon in the solid states, so it does not readily carbonize. For this reason, of the nickel chromium alloy notability in Conal 600 are used as fixture in carburizing furnace. The most common heat treatments are stress relieving, in-process annealing, full annealing, solution annealing, quenching followed by precipitation. 7. Titanium alloy. Titanium and titanium alloy are heat treated in order to reduce residual stress developing during fabrication, produce an optimum combination of ductility, mechanability, and dimensional and structural stability, increase strength, optimize special properties such as fracture toughness, fatigue strength, and high temperature creep strength. The response of titanium and titanium alloy to heat treatment depends on the composition of the metal and the effect alloying elements on the phase transformation of titanium. Like iron, titanium is an allotropic element. Titanium has a hazy crystal structure called alpha phase at temperature below 885 degrees Celsius. When the temperature of pure titanium reaches 885 degrees Celsius, the crystal structure changes to a BCC structure. The high temperature BCC structure of titanium is referred to as the beta phase, which persists at temperature up to melting point. 14.8. Other non-ferrous alloy. Heat-treatable silver alloy. The precious metals, including silver, behave somewhat similar to copper and nickel. The most important silver alloy are the silver-copper type. Copper is added to increase the hardness and strength of silver, while its effect on the electrical conductivity is small compared to that of other addition. Coin silver containing 10% Cu is the most common alloy. Fine silver is used for electrical contacts. Tableware is usually made of sterling silver and standard silver, having 7.5% Cu. All silvers alloy with more than 2% Cu can be precipitation hardened by quenching from approximately 750 degrees Celsius and aging at 250 to 350 degrees Celsius. However, this treatment is seldom applied in commercial practice for hardening, in spite of the difficulties encountered with the corrosion and brittleness of the silver-copper alloy. The only commercial application of constitutional data in the annealing of this alloy at temperature as high 600 to 700 degrees Celsius, the rapidly cooling to secure a soft condition of the subsequent cold working. The only other silver-based alloy that have been found to amenable to its hardening are the silver iridium type heat treatable goods alloys. That's all from me. If you have a question, you can write below in the comment section. That's all about chapter 40, heat treatments. Okay, thanks for watching. Don't forget to like and subscribe. Thank you.